MathSpellBook. I'm your host Peter, and basically we're going to get into some waves today. So I was looking through my favorite physics textbook, University of Physics, Modern Physics, by Young and Friedman, and I noticed that the section on waves and acoustics was just 2 chapters. Now, of course, 2 chapters could mean like it's going to be a lot of pages, but at the same time, I thought, you know what? I don't remember that much about waves, so why don't we look up the physics of waves for today's stream, and look up and basically try to find their mathematical relationships. Now, of course, like most students, we would probably start from the beginning, but we're going to be a little bit smarter about how we look at this stuff. So first, we're going to look at the summary, and because usually with textbooks, you have to, I guess, try to study more effectively, and the only way to study effectively with the textbook is that you usually start with the summary first, because that's usually where the important bits are, and with the important bits you use that as sort of like a guide to maneuver against the details there. So what we got here for the summary, so we're gonna have to keep in mind, let's see, I guess I'll read the summary out loud, since it's not going to be like a textbook. I mean, it's not going to be a whole section's worth, so let's see. Wave and their properties. A wave is any disturbance that propagates from one region to another, okay? At least we have a little bit of an abstract definition of what waves are. Because, the thing about physics is that, and I think any science does this, is that it has a way of, actually I think math and science has a really good relationship with doing this type of thing, where it's you have a word and it's defined, but it's defined to a point where it's it kind of feels like you read it once and you're like, what? But then when you actually look at a physical application or something that you can imagine or envision, it actually makes more sense. So for a wave, for us, we would think of it as either an ocean wave, or if we're more clever, we probably think of it as a wave like a jump rope, where we basically play hopscotch, and we see the rope going in a loop, when in actuality this when you look at it from a very close, probably not microscopic, but kind of a smaller zoom-in shot, you would see that the rope is actually kind of making this wave pattern as we see here in this image, while it's spinning in a loop. So basically the way to define a wave is any disturbance that propagates from one region to another. Okay? A mechanical wave travels within some material called a medium. Okay, so in this case, they're probably thinking about things like sound waves, which travel through air, and water waves that can travel through the ocean, stuff like that. So the wave speed, v, depends on the type of wave and the properties of the medium. Okay, so I'm guessing that's that equation right there. So I think we can just write that there. So we can write that wave speed. Oh, that doesn't look nice. So wave speed, and it is defined by lambda and f, and I know I'll just write lambda and f here. So I know the f is frequency, because I did read a little bit about this, but I thought I would just get a little bit more into it. So frequency, and I think they define lambda for us. So a periodic wave, the motion of each point of the medium is periodic with a frequency f and period t. The wavelength, okay, so that's wavelength here. So wavelength. So I guess we'll keep this in mind. So that's how it's opening up with this chapter. So we have to remember wavelength and frequency. Okay, so we'll just mark this with 1 here. So that way, that's the first thing we have to learn, the wave speed. Okay, and we also have something called the period. So I think we should just write that down too, because that might be important. The period. wavelength is the distance over which the wave pattern repeats. Okay. The amplitude A. Okay, we'll write that down too. Amplitude. There we go. I was like, why am I don't think that's how the spelling is. The amplitude is the maximum displacement of the particle medium. The product of the wavelength and the frequency equals the wave speed. A sinusoidal wave is a special periodic wave in which each point moves in a simple harmonic motion. Okay. So I think like within the first section we have to go over what a period is and the amplitude is. Oops. Now I am familiar with like graphs with what's it called? Trigonometric graphs, such as like sine and cosine. If you guys don't remember, I believe sine. Let's go with f of x is equal to sine x. So I think we have to go from. I'm trying to remember. Because when sine is 0, it starts here. And we go from 1 to -1 here. So if you guys are taking pre-calc or you guys are not don't remember what it was like so I'm trying to better remember here. So because I believe if it gets to 1, we're at 2, and then go down to here. So the way it works is that I'm trying to remember the exact points, like how they would define it as, because I think it goes from like pi and pi 2. Because I believe it goes like this. Well, this one should be. It has to be like at 1 at the halfway point here, and then go like this. Now I don't remember if that was from pi and pi 2. I think that's how it is. Like there's pi and pi 2, and then with cosine. Cosine is like the opposite, where it's like, well, not the opposite, but it works a little bit more like usually you would get it like this. That, but usually you would see cosine like this, where it's like more like that type of pattern, and I think that's usually what it covers here. So so let's go back to the summary here. So this one is waves and their properties, so I guess we'll just write up here wave properties. So this is just basically defined. So we have to know what the what are the parts of a wave. So it makes sense because we're actually trying to define it in this mathematical context. Now we have wave functions and wave dynamics. So we'll just write that down here. Wave functions and dynamics. In other words, the mathematical mathematical structure and why waves do what they do. Because when you first study things like motion, you have to know about kinematics, which is basically how stuff moves, and then you learn dynamics, which is why stuff moves. So basically it's saying how the mathematical way that waves work and why do they work. Let's see, your wave function y of xt describes the displacement of individual particles in the medium. Equations. This equation. This equation. Sorry, and this equation in the positive x direction. Direction. If the wave is moving in the negative x direction, the minus sign in the cosine function are replaced by a plus sign. See example 15.2. Okay. The wave function obeys a partial differential equation. The wave equation. So I think we can start off writing that one. So I think the wave equation is. We'll just use y because they show us y. So I think it's the second derivative of time v, I think that's how you write it. Oh, it's the reverse. Okay, so oopsie. So the x belongs here and the t belongs here. Alright, go. The speed of the transverse waves on a string depends on the tension F and the mass per unit length mu. Okay, so we'll start off with the wave. We'll just write that the wave equation mathematical underpin of waves. The reason why I write that is because I'm going to say that this equation is going to be like the thing that defines the behavior of waves as we discuss it. Now, of course, like I don't think I'm going to try to solve this because like I haven't gotten that part in partial differential equations, but I would say that this is sort of like I guess the theoretical way of looking at waves. That's why I'm leaving this footnote here. So I'm guessing we have these equations here. We have omega. Oh, okay, so they define omega for us too. So, because I know k here is supposed to be the wave number, and omega, I forgot what that is. I think we'll find out more about it as we go further in. So, we'll write the mainline structure. Oops, not structure. Structure for this is a cosine. I think it's supposed to be omega, right? Yeah, omega x over v minus t, right? Yeah, minus t, like so. And I think they break the equation even down, so like if we have one part of an explanation, so cosine, then 2 pi supposed to be the same up here, right? And they break it down even more by 2 pi, and they break it down with frequency, so because frequency over the speed is lambda based on the previous equation right here, yeah, because if we divide the so we have the frequency in this one, so frequency over, oh yeah, because then if it's this way and if it's reversed, then basically the lambda's on the bottom. That makes sense. So we have, oh no, not frequency, not this one. It's supposed to be lambda, and then time, and I think they break it down even more. Yeah, so it's cosine here that let's see the speed, but then it means that if we have it like this, then having this is similar to this. That way we don't get confused. So I guess they rewrote it. Yes, this, so cosine k, I think kx minus omega t. I think that's what they wrote. Yeah, I think that's what they wrote, yeah. So this equation can be broken down into a lot of things depending upon what parts are we given or what data we're given. So they wrote down that k is equal to 2 pi over the wavelength, and which I know is the wave number, so we'll just write down wave number. Omega, that is 2 pi times the frequency. So I want to see what they just find. The motion of each point of the medium is periodic with frequency f and period t. The wavelength is the distance over which, okay. So maybe we should use this picture here to help us out a bit. So we can take this picture and we can, I think we can paste it in the first part that we have here. Paste, allow please. Take this, put it over here. So we can see what a wavelength is and the amplitude. So the amplitude is here, the wavelength is here. So, oh, okay, so the wavelength is like the distance from like when it goes from one trough to the other, or depending upon where what the pattern of the wave is. I think the frequency is like the length of the wave. So basically, if you have a high frequency, it's going to go like zzz, but if you have a low frequency, it's just going to go whoop, whoop, like very slowly. At least that's what I'm guessing it is, because I is, but it has something to do with 2 pi, so I'm guessing its behavior is, maybe it's the amount of how much the frequency regresses, so maybe it has to do with, the period, like the periodicness of the period. Oh, and we also have to have the speed of, so I'm guessing this one, it involves, let's see, speed. Speed of a transverse, or what is it? Yeah, transverse wave. Transverse wave. F over mu, or F, I think is the tension. And then M and mu is the mass per unit length. Okay. It's kind of, it might be a little bit, because I do know that tension and force, like, even though they kind of behave mathematically the same, in some cases they're totally different things, which kind of makes this a little bit, like, it just irks me that they use F instead of like T, but I know why they use F, because T is representing the period here. Okay, so let's go down to the second part, wave power. So maybe we'll learn how to implement waves and use them to our advantage in that section. So wave power. Let's see, wave motion conveys energy from one region to another. For a sinusoidal mechanical wave, the average power is proportional to the square of the wave amplitude and the square of the frequency. For waves that spread out in 3 dimensions, the wave intensity I is inversely proportional to the square of the distance from the source. Okay. So I guess we'll just write those down. So we'll write average power P, that is half of the square of square and amplitude square. So basically we're taking the tension, aka force, and multiplying it by mu, which is the mass per. Interesting. Think of omega is supposed to be the pi and the frequency and the amplitude. Oh, hello, hello from YouTube. Chemicals taste good. Interesting name. What is the name of the document that you're taking notes from? So I'm taking notes from University Physics with Modern Physics by Young and Friedman. I believe you can find it online. This one's the 13th edition. But how are you doing, Chemicals? It's kind of funny to actually say your name. What's the best part of your day so far? Yeah, I'm just basically studying a little bit of physics. Because I've been doing a lot more math on this channel, and I feel like I should incorporate a little bit of physics. So we're right here, so it's proportional to the square of the wave amplitude and the square of the frequency. The wave spreads out in 3 dimensions, the wave intensity I. Okay, so we'll write wave intensity. And I think it was I1 over I2. And I think the other side it was I2 over R1. I think that was how it was written. Oh, it's the square of each. Okay, so we just forgot the square on top. There we go. Wave intensity. Okay, so we have the inverse square law here. Okay, wave superposition. Okay. Superposition. Okay, superposition. What does that mean? A wave reflects when it reaches a boundary of its medium at any point where 2 or more waves overlap. The total displacement is the sum of the displacement of the individual waves. Principle of superposition, okay. And the way they wrote it was So I'm guessing this is the, I know like when in quantum mechanics I've read in layman's terms books that they said that when you add the wave functions of every particular wave, they just become the wave function itself. So you have to actually have like a linear relationship in this case. Well, I say linear, but it's not, I don't think it's exactly linear, but the way it's structured, it looks like it is. Like every single wave function of every particle is actually going into the overall big wave function that we're trying to actually calculate for the event here. So if you were trying to calculate the wave function for a particular event, you have to add all the you have to add the wave function of every single particle involved with that particular scenario, which is not easy because there's like billions and billions of particles involved. I don't remember how many particles there are in a human being, but you have to basically, like if you're trying to calculate a wave function involving an event with yourself, you have to add all the wave functions within yourself or within the particles that make you in the wave function. And you can probably imagine what kind of an arduous task that is. Okay, and the last part is standing waves on a string. Okay, so standing waves on string. We'll just shorten that. Okay. When a sinusoidal wave is reflected from a fixed or a free end of a stretch string, the incident and reflected waves combine to form a standing sinusoidal wave with nodes and antinodes. Adjacent nodes are spaced a distance lambda over 2 apart, as the adjacent antinodes. When both ends of the string with length L are held fixed, standing waves can occur only when L is an integer multiple of lambda over 2. Each frequency is with its associated vibration pattern is called a normal mode. Okay, I think we can take this picture here. This picture actually, I like visual aids. Visual aids always help. Bring this down here. So let's see what the visual aid shows us. Just zoom in a little bit. There we go. Okay, so we got the amplitude of it spreading out, and then okay. So basically, the more the wave kind of propagates, the more you have to add, or the more that you have to multiply. So let's see with nodes and antinodes. Okay, so the A's represent antinodes and the other waves represents nodes. So the nodes are basically where it kind of like it settles down here. Alright. What else do we have? So we have, let's see, standing waves on a fixed end. And this is probably telling us the frequency. Yeah, the frequency at end. Let's see, the string is fixed at both ends. Okay. So what we have to know is that the nodes is when the string is basically like settled down, but the waves are taking place in the antinodes. We'll just write okay, that's equal to A. Multiplied by sine omega t. And this is for standing wave on standing wave on a string. On a string fixed and at x equals 0. And the next part is supposed to be the frequency. So the frequency is supposed to be r times for 2. Oh, it's supposed to be the speed. So erase this. Speed over like 2. Let's see. N can be 1, 2. I'm guessing this is how it's supposed to look for just the one frequency. string fixed at both ends. Okay, so we went through the summary, and as you can see, it took us like a half an hour to basically go over like the summary and try to question the summary a bit. Okay, so I think now we can actually get into looking over what problems they are. So these are discussion problems. I want to see the actual problems. I guess they don't have one for 15.1. Okay. So I guess for the basic one, let's see what it says. The speed of sound in the air is 20 degrees Celsius is 344 meters per second. What is the wavelength of a sound wave with the frequency of 784 hertz, corresponding to the note G on the piano? How many milliseconds does each vibration take, and what is the wavelength of the sound wave 1 octave higher than the note in part A? Okay. Alright. Oh, here's one about a tsunami. Let's see, on December, yeah, that's way back. December of 26, 2004, a great earthquake occurred off the coast of Sumatra and triggered an immense wave, a tsunami that killed 200,000 people. Satellites observed that these waves from space measured at 800 kilometers from one seacrest to the next, and the period between the waves of 1 hour. What was the speed of these waves in meters per second and in kilometers per hour? Does your answer help you understand why waves cause devastation? Interesting follow-up there. What's the hardest question here? Let's see. A fisherman notices that his boat is moving up and down periodically, owing to the waves on the surface of the water. It takes 2.5 seconds for the boat to travel from its highest point to its lowest point, a total of 0.62 meters. The fisherman sees that the sea crests are spaced at 6 meters apart. How fast are the waves traveling? What is the amplitude of each wave? If the total vertical distance traveled by the boat were 0.30 meters, but the other data remained the same, how would the answers from part A and point B and part B be affected? Okay. So I guess we'll start with 15.2 then. 15.2 periodic waves. Okay. So in this part, they basically said that the period is 1 over the frequency. So maybe we should add that so that period. So t is equal to 1 over the frequency. That's probably good to know. Which in turn is equal to 2 pi over omega. Is that what it is? Yeah, 2 over omega. Okay. The wave results in a symmetrical sequence of crests and troughs. So a crest is like when it goes up, and when a trough it goes down. Okay. Oh, they're basically using like a block on a spring to basically show us like what it means for it to go like that. Result of the wiggling. Let's see, each particle in the string also undergoes periodic motion as the wave propagates, and we have periodic waves. Now, I think I remember seeing this like in partial differential equations when they talk about characteristic lines. Like if you see like how the troughs over here, like it just shifts a little bit, but then there's like a straight line going off each trough. It's a little something that I've kind of like picked up, and I was like, oh, okay, so I see a characteristic line here, right here. Let's see what the figure talks about here. Sinusoidal transverse wave traveling to the right along a string. The vertical scale is exaggerated. Let's see, the string is shown at time interval 1/8 period for a total of 1 period. The highlighted shows the motion of one wavelength of the wave. Let's see, 3 points on the string. Let's see, the wave advances by 1 wavelength during each period. Each point moves up and down in place. The particles 1 wavelength apart move in phase with each other. Oh, here we go. Wave motion versus particle motion. Be very careful to distinguish between the motion of a transverse wave along with the string and the motion of a particle of the string. The waves move with constant speed are along the length of the string, while the motion of the particle is a simple harmonic and transverse perpendicular to the length of the string. So the waves move with a constant speed along the length of the string, okay, while the motion of the particle is a simple harmonic and transverse perpendicular to the length of the string. So let's see. I'm guessing this is at time 1, and then at time 2. Oh yeah, it basically goes like this. So as it increases in time, we have a little bit of a constant shifting here. I mean, it looks constant because it's even though it's a wave, it's kind of constant because when you look at it from a bird's eye view, it's actually going like in a straight line here, like the troughs here, or the crest, I should say. Periodic longitudinal waves. Here's an example. I think we can just try to do this as an example here. Let's take this problem and let's see if we can do it ourselves. Okay. Okay. So now let's just put our thinking caps on and let's actually try this out. Whenever I go into whenever I read a chapter and I see example problems, if it doesn't have too much overwhelming information, I usually just try to do the example problems before I actually read the answer. Oh, excuse me guys, sorry. Okay, the sound waves are longitudinal waves in the air. So we probably should read what longitudinal waves are first. Like, say, to understand the mechanics of longitudinal waves, we consider a long tube filled with a fluid with a piston at the left. Okay, so it's 15.1. 15.1. Oh yeah, here we go. Yeah. So we're thinking about this. If we push the piston in, we compress the fluid near the piston, increasing the pressure in this region. Oh, here we go. A sinusoidal longitudinal wave travels to the right in the fluid. The wave has the same amplitude A and period T as the oscillation. So we have the piston here. Two particles in the medium. So I'm guessing they're supposed to be still here, but then push the piston in. The two particles in the medium are one wavelength apart. So this is the amplitude right here. So I'm guessing when this pushes in, push out, the wave advances by one wavelength during each period. The particle oscillates with the amplitude A. Okay, so you kind of see the wave here, like, so if it's here and it's like at 0, but then you push in, this pushes back here, because I mean the fluid is going to go deeper in here, but then you basically have like that reaction where you actually like have like the equal and opposite reaction taking place here. So it pushes in. I guess I'll shake that. Then when it goes back, so I'm guessing like when it actually goes back to its original position, it will just like try to go back to its original position. But then this is actually like pushing, so it pushes in, but this is pushing this way. And when it pushes in, I'm guessing like when it pushes in, like this is like the first push, and then when it's like second, it basically tries to go back a little bit. And then when it goes back a little bit, it starts to go, try to neutralize itself back to its original spot. I'm guessing when it goes all the way back and the fluid is like back here, like it swings back side here. Alright, so let's actually get into the problem now. So, okay, so we have so this is probably the speed. In feet per second for us. What is the wavelength of the sound? So we don't know what the wavelength is of the sound in the air. 20 degrees Celsius. If the frequency, okay, the frequency is 62 hertz. And I think with hertz, it's always going to be like cycles per second. So I think we got to do the equation where it's like and frequency like this, but we're trying to figure out the wavelength. So it's going to be the wavelength is equal to V over F. And I think this is going to be not hertz. just purely just algebra at this point. So divided by, that leaves us with let's do like dimensional analysis here. So, and I'm guessing this is going to be like 1 over, yeah, because it's going to be 1 over s, because I think it's 1 cycle per second. Oh, it's supposed to be divided, and then when you have to multiply by the reciprocal, so it's going to be like this. So I think it's meters. So yeah, let's take a look at what the solution is. Yeah, so they did it the same way. Okay, that's good. So whenever we get hertz, we have to remember it's like 1 over s, or 1 over a second. That makes it much easier for us to actually think of the units that way. Like in physics, it's always important to get the units because, you know, like the wrong units can actually cost like an experiment, like amount of wasted time if it's the wrong units. Or worst off if, like, I think there was a story where a rocket didn't function because I think like it was 2 laboratories communicating with each other, but they were using 2 different units, and because they used 2 different units, things didn't work as well. And I think there was a famous train accident that's in physics books that tell you like what it's like to actually get the units wrong and what damages it could do. So okay, so at least we solved like a simple example there. Maybe we can go into the questions and actually do like the first one we were given. So let us copy this. A speed of 344 meters per second. What is the wavelength of the sound? So we are given a frequency of hertz. And corresponding to the G note, how many milliseconds does the vibration take? And from B, what is the wavelength of the sound wave 1 octave higher than the note in part A? Okay, so we have to figure out the wavelength of the sound. So we don't know the wavelength, so that's going to lead us to our equation V over, and the wavelength should be, take out my trusty calculator, so if we type that in, that would be 2.78 meters. Okay, so that solves that one. Now, how many milliseconds does each vibration take? Okay, so now we have to figure out the time. Okay. So we got meters per second. Yeah, so we got meters per second, and then we got wavelength. Somehow from these numbers we have to discern a time. But how do we do that? originals here. So let's see. So we probably should remember omega and the period. So omega is 2 over the frequency, and the period is 1 over the frequency. So I think the period should allow us to get the time in omega. Let me read deeper onto what it says here. Let's see the frequency and angular. Oh yeah, so we also have to remember that this is 2 pi over omega, right? Yeah, over omega. Okay. So how can we use these numbers to help us here? Well, actually, let's define what a period is, because I think once we period. Because I want to actually use the definitions to like kind of give me a clue of what I'm looking for and making sure that I'm looking for the right thing here. Let's see, a more interesting situation develops when we give free end of the string a repetitive and periodic motion. You may want to review the discussion of periodic motion in chapter 14 before looking ahead. Okay, chapter 14, huh? Periodic motion. Okay, here we go. Restoring force, amplitude. Here we go. Period. Period that is the time of one cycle. It always positive in SI units. Okay. Seconds per cycle. So, oh, here we go. So basically the period will be the time, because it basically is how many does each. Okay, so I'm thinking that's what it means. So I think we have to actually calculate the period here. So the period would be, and then frequency is 784. So that is, I think, seconds, right? Yeah, it calculates in seconds. So I think we have to actually multiply this by milliseconds. So we have 1 second here, and milliseconds, I think, is 1,000. Why am I writing microseconds? It should be milliseconds. I forgot what the unit was for milliseconds, but we'll do that. So it's 1.27 milliseconds. And I think that's A. So that's A. And for B, we have to write down for B here. What is the wavelength of sound one wave octave higher than the note in part A? Dang, I forgot what an octave was. Octave. Oh, we have simple harmonic motion. We'll probably end up going back and forth with this chapter. Because, yeah, I mean, that's what happens when you skip around. But I'm pretty sure we can handle it. Let's look at the index. Looking for O for octave. Oh, we're at the O's. Octave. Does it have something to do with 8? Like 1 over 8? It might be, because we have like a little bit of... Let's see. Figure shows part. What does it mean by octave? So, what is an octave? The interval between two notes, where the higher the note has twice the frequency of a lower note. Let's see. The interval between two musical notes, where the higher note is twice the frequency of a higher note. So, based on our question, it says, what is the wavelength of the sound of one octave higher than the note in part A? So, let's see, a ratio of 2 over 1. So let's see, the note of an octave above it will have a frequency of 2F. Okay. So 2F, huh? We'll just write that as an octave. So if it has double the frequency, then that means it's going to be, I think it's going to like have a faster period, I think. Because let's see, the period, well, it's getting closer to 0. So then it'll be probably, yeah, it's probably going to be like much closer to 0, hence going to be much, yeah, it's probably going to have to take less time. So what is the wavelength of the sound? So in this case, we're going to have the new wavelength. We're going to call it wavelength N. So in that case, we're just going to have to take our same numbers, but then the frequency is going to be increased. It's going to be multiplied by 2. At least I hope that this is the right way to calculate it. And that leaves us with a wavelength of 2.1 Yeah, so it takes less time because it's less distance. What is the wavelength of the sound at the higher note? So it's reduced a lot, actually. That is if we're doing it right. Oh yeah, we should open Quizlet because we do have this book in Quizlet. Library, folders, physics, physics 13th edition. Here we go, and we're on chapter 15, mechanical waves. Bring this down here so you guys can see it, and I think we'll just move it over here. We are working on problem 1. Oh, I think this is discussion questions. Exercises. Here we go. Exercise 1. Oh, did we make a bad? Maybe I didn't put the right numbers in. Let me see. So dot 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 7. Oh, oops. I guess I put the wrong numbers in. How did it turn out that way? Okay, so the difference is a little bit. Okay, that makes it more manageable, actually. Alright, so... Well, the technique was correct, so... Okay, 1.28. Yeah, we got, like, close to it, so that's pretty good. Now for exercise B. Hopefully we did this right. And I think, yeah, 2.28. It's relatively close. It's relatively close. Yeah, I mean, that's practically the same thing to do. Yeah, because the way they did it, like, I thought it was kind of funny looking, but it looks about the same. Yeah, it's practically like the same. Oh, I think I wrote, I think I meant to write 2 here, not 8. I think I wrote 8 because I saw the 9 like after the 1. I think that's the reason. But I think our technique was the same. It was pretty much the same. We just got the wrong number here because for some reason, I don't know why. Maybe I put a 0 in between or something. But the technique was still the same, so we managed to get that. Okay, so we learned a little bit more about that. We learned what an octave is, and we started to see the implementation of the period, which I think is really, really good. Okay, so let's try another one. Let's try another one, shall we? Questions, exercises. Okay, so what's number 2? How long is number 2? Oh, number 2 looks so long. Might as well do it. So first we'll copy this half at the bottom, and then we'll paste it here, and we'll just expand it here, and then we'll copy the rest of it from this side, like so. There we go. And then we'll paste it over here. And I think we'll just put it down here because it's still technically like just connected like that. There we go. And then we'll expand it like so. There we go. I think we can just shrink it to make it look properly straight. Oh, that didn't line up. Line it up a little bit like that. I'm just being a stickler here. Almost a little bit right there. Yeah, cool. It looks like they're connected now. Almost. I can see this little dent here, but that's fine. Let's see. Providing the amplitude is significantly great, human ear can respond to the longitudinal waves over a range of frequencies of about 20 hertz. Okay, so we're given 20 hertz. So that's the frequency, 20 hertz, to about 20 gigahertz. Oh, okay. So that's a range. So we'll just write that for, for like what the information is given. If you were to mark the beginning of each complete wave pattern with red dot for the long wavelength sound and a blue dot for a short wavelength sound, how far apart would the red dots be and how far apart would the blue dots be? In reality, would the adjacent dots have in each set be far enough apart for you to easily measure their separation with a measuring stick? B, suppose you repeat part A in water where sound travels. Okay, so we'll just put in water. Speed of sound. Speed travels at meters per second. How far apart would the dots be in each set? Could you readily measure their separation with a measuring stick? Okay. Alright, so I'm guessing one is like one of the blue, let's see, mark the beginning. So I'm guessing longer wavelengths are red and shorter wavelengths are blue, because I'm thinking of the Doppler effect. So 20 hertz, if we have a speed that goes over 20 hertz, then that means if our speed is faster than like at least 20, then that means it will basically go, we'll have a longer wavelength, right? Yeah, we'll have a longer wavelength. So in order for it to have a shorter wavelength, we're gonna have to have we'd have to go closer to 0 at that point. Because the wavelength is basically the speed over the frequency. So I'm guessing 20 hertz is reflectant of maybe the red wavelength. And then, so let's just, so we'll say red is, so the frequency for the red one, I think it will be, I think it will be 20 hertz. I mean, my logic might be mixed up, but we'll just try to see how it goes. 20 gigahertz, which in turn, let's see, 20 gigahertz. If you were to do the math on that, kilohertz is like 1 kilohertz is 1,000 hertz. So if you do that, that's 20,000 hertz. Okay, so I'm guessing now we're just gonna have to calculate the wavelength of these waves. If you mark the beginning of each complete wave pattern with red dots for the wavelength of sound and long wavelength of sound, and the blue dots for the short wavelength of sound. How far apart would the red dots be? Okay, so now I have to remember what was the speed. What was the speed of sound and air? Because I think I think that speed is necessary in this case. Did it say anything in the periodic motion? Because maybe they talk about the speed of sound at some point. Or maybe I should look at the index. Maybe this is what it's like to be a scientist. It's like you're given information and you think like you feel like you're on the right track, and then you're just back in the books or on the internet just looking up stuff, or like in the research archives. Spring, here we go. Speed of light. I need the speed of sound though. Speed of supersonic sound waves. Here we go. 518. So 514 to 518. 114. I don't think it's gonna lead me to the right page, but okay, yeah, this one's like far, so we're gonna have to go all the way down. Oh, it's not even here. It's not even in this chapter. Well, let's look it up anyway, because let's see. 512, 513, 514. The speed of sound waves, okay. So for this question, because I need a speed. I need a speed for this reference, so that way we can calculate the wavelength. But then again, I don't want to make up a number like 1 meter per second. But then again, that could be easier though. I guess we can do that. 1 meter per second. Because at this point, it will give us a difference. So let's calculate the red wavelength, because I think that's going to be a, let's see, 20 hertz. That's around 0 point meters. And for the blue one, just leave them different colors so that way we can is 0 point. Well, actually, we can write in scientific notation. So it's 5 point times 10 to the 5th meters. So this is a much shorter wavelength. How far apart would the red dots be, and how far apart would the blue dots be? I mean, minus this from this. Guess we'll put in white the difference between them from red a difference of 0.5 meters. Which is practically like about like it's practically like half at that point. Interesting. So I guess you can measure it. In reality, would the adjacent dots in each set be far apart for you to easily? I think so, but not that much. Suppose the repeated part of A in water, the sound travels at, okay. So now we actually have to do it in water. So let's go down here. I mean, this counts as A and B. So C, we're given the speed of sound in water. Now, when we do it for the, let's actually calculate this for, because we have to calculate what, how far apart are the dots, so we have to calculate the wavelength in water. So if we have divided by, so this one is going to be 74 meters, and for the blue one it'll be 20,000 hertz, so it's going to be 0. meters. Double check my numbers here with the previous one. Okay, yeah, the numbers are about the same. Alright, so for this one, yeah, you could definitely measure this with a measuring stick. Because we're left 1 divided by 20, that's 74 meters for the wavelength. And then if you do it with because that's 20,000 hertz. Yeah, that's around like, yeah, like 0.0. Oh, oops. Should be another 0 there. 0.0. There we go. That's what we want. How far apart would the dots be in each? Could you readily measure them with the separation of a measuring stick? So the difference between these two, I think the difference is really huge with this one. So red, it's practically about like, that's the difference. Wow. So it's like basically like it's like 10 times. Almost, yeah, practically 10 times. Or 1,000 times, I should say. Because like if you divide yeah, it's practically 1,000 times. It's like 1,000 times the difference. I mean, like, there's like 1,000 times difference between them. That's pretty interesting. Now, let me check. This one's number 2. Now, I don't think we answered these like in the way they kind of expected us to, but we're going to give it a whirl and see what it comes up with. Hey Goofy the Ultimate. What's the best part of your day so far, my friend? Oh, they do centimeters. Okay, we got that result. And okay, yeah, they changed it to centimeters at this point. What did they do here? Oh, they did use the speed of sound. Okay. That's why it's off. That's why my numbers in the first one were off. Okay. Because, like, I was like, did they give me a number? Or I didn't see it. No, they didn't give me the number. I guess you're supposed to know that the speed of sound is that. Oh, it's because of the first problem. Okay. Because it says at 20 degrees Celsius, and I'm like, I mean, I guess we'll take it the way it is. Yeah, because, okay, so we're supposed to use this number. Okay, that's the reason. Okay. I mean, our thinking process was right. It's just that we didn't have the right numbers. Oh well. I mean, at least our thought process was right. We just had to have the right numbers, though. But I think technically we would, like, I mean, we didn't get the numbers right, but at least we got the thinking right, and I think that's fine. We're applying basically wavelengths, and like, you know, because actually the first question I actually liked because it allowed us to take our knowledge of periods, and we actually got the time, which I thought was pretty cool. Okay, I think like, even though we did get this problem like numerically wrong, I think it's kind of like, you know what, I'm satisfied because we learned a lot from this one. Because we know that our thinking was right, it's just that we didn't have the numbers. Or I didn't have the numbers. I should have known that 344 meters per second is the sound is the speed of sound in air. But, you know, that's what happens sometimes. But at least the thinking was correct, though. But I'm not gonna make that like, you know, like something like, oh, now I know waves now. No. I'm just basically saying that, hey, at least my thinking was correct here. So the technique was right, it's just that numbers were off. Which usually happens to me whenever I do problems sometimes. It's like, whenever I get a problem wrong, it's always the wrong numbers. It's never really like the technique sometimes. But I still get discouraged because I know I got it wrong because of the numbers. Which kind of makes me feel like I shouldn't be a scientist or an engineer, because you have to make sure your measurements are precise. But then again, like, I don't know how many engineers or scientists get the numbers off by like a magnitude of like 5 or 10, like in the laboratory. Okay, what do we got here? Tsunami. We read this question already, so a satellite observes that the waves from space measured from one wave crest to another. So I'm guessing this is the wavelength here. The next period between is 1 hour. Okay, so we're given a period this time. So we're given a period of 1 hour. So I think it's time we just basically convert that to seconds. And I think that's seconds there. So I think we should just write that many seconds. I don't know why I did the conversion, but I think that's how I think of it in my head. Even though I shouldn't have to. And I think we'll convert this. So I think this is the wavelength. So, because it basically says the satellite observes that these waves from space measured 600 kilometers from one wave crest to the next. So yeah, I think that's the wavelength. So if we have, and then from 1 kilometer to 1,000 meters. I'm just typing in my calculator because I want to make sure that I have the right amount of zeros. Because whenever I write these, I sometimes miss the amount of zeros, and I really hate it when that happens. Okay. So, what is the speed of these waves from meters per second and to kilometers per hour? Okay. Oh. Well, at least we converted early. Because usually whenever I do a physics problem, I always make a habit of converting it first if it's like in different measurement, if it's different systems of measurement. Does your answer help you understand how devastating waves are? I think it will. So the equation we have here is the speed times the wavelength times the frequency. Now we don't have the frequency, but we know that the period is 1 over the frequency. So what we need to know is that the frequency, or implies that the frequency is actually 1 over the period. So we can replace this. So we can replace this by saying, aha. So now we'll do it for the first one for meters per second. So we're given 800,000 meters over 3,600 seconds. Ooh. I just rounded it up, so basically it's just a bunch of twos. It's like 222 meters per second. So if we do that for, we'll just put this SI, and then we'll put this in imperial. So we'll just put an I there. Okay, so now we got to do it for an hour. That means it's going to be 1 kilometer per hour, 8 kilometers per hour. Ooh, that's fast. That's very, very fast. I mean, if we go on Google and say, what is the equivalence? What is the real world equivalence? I'm forgetting how to spell equivalence. There we go. Equivalence to, let's say 100. Let's say 100 meters per second. Let's go with that. That way we'll get a good category. Okay, so 100 meters per second is equivalent to approximately 229.7 miles per hour. So it's over 200 miles per hour waves hitting you. that is devastating. That is devastating. Yeah, so a speed of a cheetah could probably go up to 98 to 112 kilometers per hour. So that's faster than a cheetah. Wow. Wow. Let's check if we were correct in our thought process with that. So, number 3. Yep, we got those numbers correct. Those what we got. Awesome. We're doing pretty well. Doing pretty well with this. So let's try the next one. Let's try the next problem, so we can enhance ourselves with more knowledge here. So this one's an ultrasound problem. These problems are actually pretty fun because I think I like problems that deal with the stuff that we can't see, such as waves. I mean, like, it's cool to deal with forces and stuff with physics, but sometimes I like to do the stuff that seems kind of like beyond the human sight. So I find it very interesting that waves have this type of power. But you guys can tell me what you guys think in the chat about waves. Pardon me, guys. All right. So what do we have? Sound having frequency above the range of human hearing, about 20,000 hertz, is called ultrasound. Okay. Waves above this frequency can be used to penetrate the body and produce images. Oh, okay. By reflecting from the surface. Okay. I guess that's why they call it ultrasound, because they just use sound that we can't hear to basically get images from the body, which is pretty cool. In typical ultrasound scan, the wave travels through the body tissue with the speed of 15,000 meters per second. Oh, okay. For a good detailed image, the wavelength should be no more than 1 millimeters. What frequency of sound is required for a good scan? Okay. So we need a wavelength of that much. So first off, we know that the wavelength is millimeters, but we're going to reduce that to meters, so that way we can just get the measurements correct. Given a speed of, so what is the frequency of sound? Okay, so we have to have the frequency. So the speed we need is here. Now we have to figure out the frequency. So the equation we're left with is the wavelength times the frequency, right? So the wavelength times the frequency. So now we have to figure out what the frequency is. So the frequency will be equivalent to the... Oh, okay, so this is like our first problems. Okay, so the frequency will be... Let's see. 15,000 divided by 0.001 meters. Ooh, the frequency has to be... Let's write it in scientific notation. It's not ultra huge, but I just don't want to write the zeros. 1, 2, 3, 4, 5, 6 meters. Or I should write hertz, because this is in meters and this is in meters per second, and then yeah, so it's 1 cycle per second. So wow. That is really, really fast. That's a really fast frequency. And that's in an ultrasound, guys. That is a lot of hertz. No wonder it costs a lot of power just to see inside your body with those machines. So this is number 4. So let's see. Number 4. Okay, hopefully we did this correctly. Yep, we got it right. 1.5 10 to the 6 hertz. That's a lot. That's a lot, guys. It shows you how far we've come in science. Don't you agree? But that's cool. That's really cool, actually. We learned a little bit about ultrasound. That's really, really cool. I love that. Alright, let's see what this one does. Okay, audible wavelengths. Okay, what do we got here? The range of audible frequencies is from about 20 hertz to 20,000 hertz. Okay, what is the range of the wavelength of audible sound in the ear? Okay, so we want the wavelength. Okay, I think we calculated that many times. But now we know that the speed of sound in air is 344 meters per second. So we'll keep that in mind. So the frequencies we have range from 20 hertz to 20,000 hertz. Oops, see. 20,000 hertz. Now it's asking what is the range of the wavelength. So in this case, the wavelength is like this. So for 20 hertz, I think we already calculated that already, but we'll do it correctly this time. So that leaves us with 17.2 meters to. Okay, so if we take the speed of sound, take 20,000 hertz, that's 0.0117 meters. So the more the frequency increased, the less the wavelength doesn't extend as much. So that's a good behavior to take in mind. So what is the range? So this is A. That's the range. Now for B, it's asking what is the range of visible. What is the range of visible frequencies of light? Oh, it says more up here. Okay, visible light. The range of visible light is extended from 400 nanometers to 700 nanometers. Anything below millimeters, I have to go back and review. So nanometers to meters. Okay, so a nanometer is about 1.02 -9 meters. Okay. What is the range of visible light? So I'm guessing it's asking what is the wavelength of visible light. Okay. Oh, that's cool. So basically it's having us measure this. Great. Now we're going to have to actually use the speed of light, which is going to be cumbersome to deal with. Okay, but I think I remember what it was. So the speed of light is 2.299 million. Per second. I think that's how the speed of it. I like either these numbers are switched around, or or either I'm correct or the last 6 digits are switched around. 299,972,458 meters per second. I'll probably find out when I'm calculating this. So now we have to calculate the wavelength of these. So divided by 1.9 or to the 11. Should be right. it by hand. Nanometers, and then 1 nanometer. Oh yeah, you have to multiply it. Okay, that's good. That's good to know. Okay. Okay, 400 times 10 to negative. Yeah, so it would be 4 to the negative 7 meters. And I think it would be the same for 700 nanometers. Okay, times that. Oops. And 10 to the negative 9. Yeah, so it's about the same. In like digits of 10. So now we gotta calculate the wavelength of it. Well, not the wavelength, the frequency. Right? Or did I calculate the wrong thing? Let me see. Visible light extends from nanometers. So I think that is the wavelength. Yeah, because that's a distance, so we have to calculate the frequency now. Okay, so the frequencies, and the frequency is, so this will calculate the speed, so then the frequency will be equal to the velocity. Okay, so now we'll take the speed of light, with the frequency of, we'll round it up to 5.5, 7.5 hertz. That's for 400, and 2. Let's do it for 700. So. So what we got here for brain surgery? Surgeons can remove brain tumors by using the Galvatron ultrasonic surgical aspirator, which produces sound waves of frequency of 23 gigahertz. What is the wavelength of these waves in air? Okay, so I guess we're doing the speed of sound with the frequency. Okay, so the speed of sound is 3 meters, and we're doing the frequency, which is how much? 23 gigahertz. So 23 gigahertz. So 1 gigahertz is 1,000 hertz, which means we're going to be left with 23,000 hertz. asking for the frequency for the wavelength, right? Yeah. What is the wavelength of it in air? Okay, so the wavelength in this one, I think that will leave us with, divide that by 0.4 meters. So that's the wavelength. And I think we have another question here, which is D. Sound in the body. Okay, what would be the wavelength of the sound in part C? In bodily fluid, in which the speed of sound is, oh, okay, but the frequency is unchanged. Okay, so we have the frequency, so, oh, basically like in fluid. So in fluid, so that's another thing we can to learn, is that the speed in fluid is 1 meters per second. Is that it? Yep. Okay, so the numbers to keep in mind when it comes to like this type of stuff, I think is really cool, is that we have to remember that 3.344 meters per second is the speed of sound in air, whilst 1,480 meters per second is in the speed of sound within a fluid. So that is really awesome knowledge to know. So the frequency is still the same, so hertz. So now for the frequency, for the wavelength, we are given meters. Okay. That wasn't too difficult. Now let's check. So this one is number 5. So number 5 part A. Yep, we got those numbers. Yep. We got them in the reverse order, but we got them nonetheless. For B, where did I put it? Okay, here we go. 0.5 hertz. Did I miss something here? Okay, so. Oh, they, but then again, did I miss the decimal points here? Maybe I multiplied it by mistake, did I? Let me double check here. The velocity. I used the exact number of the speed of light. Oh yeah, Yeah, there is exponents. I didn't see at the end. Because there were so many digits, I forgot to write the exponents. So this is supposed to be 10 to the 14th hertz. And I think it's supposed to be 10 to the 14th hertz too. I forgot to look at the exponents at the end. That's a lesson to myself, just to check if there are exponents afterwards. But okay, so I showed all the steps. I just showed the answer here. Point meters. Yeah, that's right, because it's like -2. 10 to the 2 to the negative 10 to the -2 meters. Yeah, that's correct. They wrote it in scientific notation. And for D, you have 0.6. Yeah, 0.6 meters per second. Okay, so I feel like we achieved a good amount of progress there, because like we actually, I mean, we didn't solve the last one, but we'll probably do that tomorrow. But yeah, we actually covered like a lot on waves today. And we learned a little bit more about the relationship between the frequency and the wavelength and the speed, in addition to the period of the wave. So the period is actually very important, actually. And actually has a good relationship with the frequency, so we learned more about that too. So that's actually really good to keep in your pocket. And we learned a little bit about ultrasound, which I think is really, really cool. So I think today was a really good day to actually like engage. Like I think with physics, you actually began to learn more about the stuff that maybe you've taken for granted, like medical and all that stuff. So I think that was really cool. Which goes to show that science is very diverse. You know, like people go to medical school to basically be better doctors, but you know, to be like, you know, to actually have the scientific knowledge about like, you know, how things work. I think that's the thing that really makes a doctor more effective when it comes to the physical world and its relationship to the body. So I think that's really, really cool. Okay, guys, practically, I think that will do it for today's stream. If you're watching this on YouTube and you like math, physics, or just hey Deku Spoon, I was actually about to end stream, but like thanks for like coming in like at the last minute, and so that I can say hi to you. What's the best part of your day so far, Deku Spoon? But yeah, if you guys like no differential equations tonight, no. Actually, I'm working on more physics stuff today, so I guess it's more applications based. So we actually did some waves. Hey Van Fox fan, dang, you guys show up like just when I'm about to end stream. No, it's okay. It's okay. This stream will be uploaded, so like if you show up like late, you know, you'll be able to catch it on the YouTube channel. But yeah, if you guys like math, physics, or just need a study stream to like keep yourselves productive during the stuff that you need to get done, you know, drop me a sub in YouTube, in addition to leave a like on the video. In addition, like if you're watching this after the live stream, leave a comment down below to see what subjects you guys would like to see me do on involving physics and mathematics, if that interests you. Because maybe I'll probably take a dive into it and take a look. In addition, if you're watching this on Twitch, you know, drop a follow. It really helps out my channel. And for all those that are watching on YouTube, the links to the Discord as well as a link to my Twitch channel is down below if you want to check that stuff out. In addition to a link to my video game channel as well. And I think on Twitch I'll post those up for you guys so you can see. So I will put up Discord, and I will put up my video game channel, my Uncle Talks channel. We're gonna actually have a podcast today if my co-host is actually available today. So if you want to actually check out our podcast, it's not going to be talking about just math. It's going to be talking about just life in general, like what's going on in our lives and, you know, the stuff that we find interesting. But yeah, thanks for joining me today, guys. And always remember, everyone is precious. You guys are just as precious as everyone else. And I will see you guys tomorrow for the next stream. So take care, guys. Bye-bye.